All right, in this video we're going to talk about standing waves. So let's go ahead and get started. So what is a standing wave? Well, it's a wave that appears to stand in one place, even though it is two waves interfering as they pass through each other. So really it's two waves interfering, but the way that they're interfering is so perfectly timed, it looks like the wave is standing still. So it's formed as the result of the perfectly timed interference of two waves passing through the same medium. So it has to have the same medium and it has to be perfectly timed. A standing wave pattern is not actually a wave. Rather, it is the pattern resulting from the presence of two waves. Sometimes it could be more than two waves of the same frequency. So that's very important. The two waves or three or four waves has to have the same frequency and with different directions of travel. So one traveling to the right, one traveling to the left. So in our animation here, it looks like our orange wave is traveling to the right, our blue wave is traveling to the left. They have identical frequencies, which is how they are able to create that green standing wave, where the wave literally appears to just be standing still. All right, here's another example where our red and blue waves have the exact same frequency. In this animation, the blue wave is moving to the right, the red wave is moving to the left, and then the interference of those two waves is creating this black standing wave. It's not really a wave, but it appears to be a wave that is just standing still. But in order to have a standing wave, the incoming wave and the reflected wave have to have just the right frequency so that they combine. So in this simulation, I created an oscillating wave. So I'm sending the wave to the right, and as it gets to the fixed end, it gets reflected back down. And it gets reflected at the exact same frequency. So the same frequency is being applied by the oscillator and by the fixed end, so it appears to have a standing wave. Now for these waves, there are, of course, properties that correspond with these waves, nodes and antinodes. So a node occurs when the destructive interference produces points with zero amplitude. So a node is areas of destructive interference. So destructive interference has zero amplitude. So these nodes are actually areas that look like this. So these are both nodes. In this bottom diagram, this is a node, this is a node, this is a node. Anywhere where it is in the rest position at a zero amplitude. On the other hand, you have antinodes, which of course is the exact opposite. So an antinode occurs with constructive interference. It produces points with an amplitude that is greater than zero. So it has an amplitude. So these antinodes are located here, here, here. On this bottom diagram, the antinode is located here and here. So it's the crest and the troughs essentially. So the way that I remember it is that nodes have no amplitude. There are areas where they cross the rest position. Antinodes have an amplitude, A and A. Amplitude, antinodes. So it is the highest point on the wave and the lowest, the crest and the trough. Okay, and here is a real life example for you. So where you would actually see standing waves and the interference of two or more waves coming into your real life. So imagine you're setting up a room and you want to have a loudspeaker, and of course when you watch a movie or your favorite show, YouTube videos, whatever it is, you want the sound to be crystal clear, you want it to be loud, you don't want weird echoing, so it matters where you place that loudspeaker, right? You kind of have to test it out. Well, you're actually trying to determine where to place the loudspeaker so that you have in face instead of out of face. So what that means is the loudspeaker is first sending out the wave, and as the wave goes outward, it has to travel to hit the wall, right? But it's hitting a wall. So of course that wall is going to make a reflection. So this red wave is that reflected wave. And what you should be seeing for this reflected wave is it's destructive interference, right? It's out of phase. So with this destructive interference, that's going to destroy your sound. So this is going to cancel out your sound. This is also what noise canceling headphones use. This is the same mechanism. So you wouldn't want to keep your loudspeaker there. You would actually need to move it, right? So you move it back some, you change its position, and finally you get it in a position that's the perfect distance away, the right angle, and when the loudspeaker does end up sending a wave outward for you to test it, you send out the wave, and it has to travel to hit the wall. When it hits the wall, again, it's going to be reflected back, but the way that it hits, it reflects back in phase, and you'll notice it's the exact same amplitude, the exact same frequency, and it's a true reflection of your original wave. So this is an in phase, and it results in the increase in amplitude. So the blue wave is your constructive interference. This is constructive interference happening in real life. This is how you would amplify sound. You would need constructive interference so that you can increase the amplitude, because remember, amplitude is tied to the loudness of sound. All right, that's it for today. Thanks for watching.